Okay, this video is for lesson 6.3. We are dividing radicals in this lesson. So we had a rule when we were multiplying radicals. We learned that we had to check to make sure the index was matching. That's the type of root. And if our index was matching when we were multiplying, we could multiply coefficients or the outside parts of the radicals together. And we could multiply the radicands or the inside parts together. Make it one radical term and then simplify it. And it's very similar when we're dividing. So we have some rules when we are dividing with radicals. The big thing is that we are not allowed to have a radical in the bottom, okay, in the denominator. Okay, this is a big no-no in algebra. No radicals are ever allowed in your final answer. So you have to figure out how to get rid of that radical term in the denominator. And there's a few different ways you can do it, and it just depends on the problem, and we'll talk about steps to recognizing how to get it out and what's the best method. So for the first 4 examples that we have here on our notes, they will all be simplified in the same way. One way, and kind of like the easiest way to get rid of a radical in the denominator, is if it gets like divided into the numerator or absorbed into the top term. And then we no longer have a denominator to worry about. So let's look at number 1. We have 12 square root 160, and we're over 2 square root 5. So because they're both square roots, we can try to put these 2 radical terms together. We can divide our coefficients. Just like our coefficients multiplied, our coefficients can divide into each other. 12 divided by 2 is 6. And then we're going to say square root, and underneath we have 160 and 5. We can divide those. 160 divided by 5 is 32. So we kind of sucked up that denominator and divided it into the upper, like that numerator on top. And we made it one radical term. So now we want to simplify this, and this is what we've been working on the last couple lessons. How do we simplify this radical? Because it's a square root, I would use my perfect squares. Remember, our process is take half of the radicand. Half of 32 is 16, and 16 is a perfect square. So we can think of this as 6 is on the outside, but 32 is the same thing as 16 times 2. Because 16 is a perfect square, we can square root that factor of 32. The 16 comes out as a 4. Because there's already a 6 on the outside, they multiply. 6 times 4 is 24, and we're left with the square root of 2 as a remainder. There is no denominator to even worry about, so we are all good. 24 square root 2 is a simplified answer. Okay, on number 2, we have 36 fourth root of 1250 divided by 9 fourth root of 2. Again, we're not allowed to have that fourth root of 2 in the denominator. No radicals in the denominator. So we can see if we can simplify the denominator into the numerator. So we check 36 does divide by 9. It makes 4. And then we're going to make a little fourth root house here. And we can take our 1250 and divide it by 2, and we get 625. Okay, the denominator got divided into the numerator, so now we have one radical term to simplify. Because this is a fourth root, you're looking at your fourths list. And 625 is on your list of perfect fourths. So we don't need to break it down any. Just remember that the fourth root of 625 is 5. So 5 comes out. There's no radical on it if it comes out. We multiply it to 4, and the answer is just a nice, neat little 20. Okay, now we're dividing with radical terms. We have the square root of x cubed y to the 9th power divided by the square root of x squared y to the 5th. Now, all these variables are underneath the radical, and we can apply our quotient rule. When you are dividing with variables, you subtract their exponents. And we do our top minus our bottom. So this would equal, I'd make a square root house, because they're going to stay inside for now. We have 3x's minus 2x's, which makes 1x. And then we have 9y's minus 5y's, which is y to the 4th, or 4y's. And then we would simplify this radical. For variables, to take the square root of our variables, we divide their exponents by 2. So when we do variables, I make the 2 little houses. Now x is to the first power. 1 does not divide by 2, and it never will, so we kick that whole thing out. Our exponent is smaller than our index, so we put it away. Now y to the 4th is a perfect square because all even exponents divide by 2, so they're perfect squares. And then we let y to the fourth out by dividing by 2. That's how we square root our exponents. So we have y squared on the outside, square root of x on the inside. And we're finished. Number 4, we have some cube roots we're simplifying. Okay, check your outsides, your coefficients. 28 divided by 4 is 7. And we have the cube root. Underneath, we can do negative 16 divided by 2 is negative 8. And for our m's, we have 6 on top and 1 on bottom. 6 minus 1 is m to the 5th. Now we need to simplify the radical. So bring down our 7 on the outside. We have the cube root, 2 cube root houses. Negative 8, or 8, is on your perfect cubes list, and we can cube root negative numbers. So we're going to put negative 8 in the first house. Now, to cube root our variables, we have to divide the exponents by 3. But 5 doesn't divide by 3. 4 does not either, but 3 does. So we keep 3 in the first house. That's our perfect cube house. That left 2 in the second. Remember, 3 plus 2 makes 5. It always adds back to the original. And we're going to cube root our first house. The cube root of negative 8 is negative 2. And we divide our exponent of 3 by 3 since it's a cube root. And we get 1m that comes out. We multiply that to 7. So we have negative 14m. And we bring down the cube root of m squared. And again, one way to know that you're finished is that the exponent underneath the radical can never be bigger than the index. It has to be smaller. Otherwise, you did not take out enough variables. Okay, on these next few examples, 5 through 8, we have a little bit different way to solve. So we'll go over that. On number 5, notice our radical, the square root, goes over the whole fraction. And that's okay. It means the same thing as what we did in the first 4 problems. We have the square root of 48 over 16. And I would still check, does 48 divide by 16? And it does. 48 divided by 16, okay, is 3. So we have the square root of 3. Now 3 is our radicand. 3 is a prime number. We can't break down prime numbers. So that's one way to know that you're finished. If the number, that's the radicand, underneath the radical is prime. There's nothing else you can do. We can't change our prime numbers. Okay, number 6, we have, though, the cube root of 40 over 27. Now, we have the radical over the whole thing. We're hoping that 40 and 27 can work together, that they can simplify each other, in other words. So I would check, does 40 divided by 27, do they reduce in any way? Okay, and they don't. It just stays 40 over 27. So here's my thing. If they cannot work together, that's our first check, and it worked on numbers 1 through 5, but not working anymore. They can't work together. We have to break them apart. Give them their own space. Simplify them separately. So I would say this is a cube root of just 40 over the cube root of 27. Because maybe they don't work together, but they work really good on their own. Okay, now let's simplify our numerator. The cube root of 40, we can think of what perfect cube goes into 40. It's 8. 8 and 5. So we break it down to 8 times 5. Now the denominator, 27 is a perfect cube. The cube root of 27 is 3. So 3 comes all the way out of the radical. It was a perfect cube. And then in my numerator, we take the cube root of 8. Cube root of 8 is 2, so the 2 comes out. So our final answer is 2. We left the cube root of 5. That stayed in, and it's all over 3. And that's simplified. Notice there's no radicals in the denominator. Okay, 3 is just an integer. That's the way we like it. Only radicals in the numerator. And that numerator has been fully simplified. So it looks like we are doing everything correctly. Okay, on number 7, we have the cube root of 7x to the 5th divided by 64y to the 6th. So the first thing I would check, does 7 over 65 reduce? Can they work together? Can they simplify each other? And they cannot. So we're going to leave them the same. And then the numerator, we have x to the 5th. The denominator has y to the 6th. They have different letters. So again, these two, numerator and denominator, they cannot work together. So we are going to let them work separately. So I'll write that as the cube root of 7x to the 5th over the cube root of 64y to the 6th. And I will simplify each of these terms. Now, 7 is a prime number, so I'm going to break the numerator apart into 2 cube root houses. 7 is prime, so we're going to kick it to the little reject house. But x to the 5th, 5 is bigger than 3, so we know we can break it down. And we're going to kick out 2 x's, because if we leave 3 in the first, 3 divides by 3 evenly. We can reduce that. Over. Now let's look at the denominator. What changes can we make here? 64 is a perfect cube. So is y to the 6th, because it divides evenly by 3. So cube root 64, we get 4, and 6 divided by 3 makes y squared come out. To finish it off, we go back to our numerator. We cube root our x cubed. 3 divided by 3 is 1, so 1x comes out. So our final answer is x cube root of 7x squared divided by 4y squared. Again, we don't have any radicals in the denominator, and the ones in the numerator are fully simplified. Okay, the last one in this section, we have the 4th root of 32w divided by 81. So check, does 32 and 81, do we have any common factors? Can we simplify these at all? And if you tested it in your calculator, your Casio 32 divided by 81, it would actually just stay the same. So again, they can't work together, so we'll split them apart and let them work separately. So the 4th root of 32w over the 4th root of 81. All right, now let's look at our perfect fourths list. You should have your note card with all your perfect squares, cubes, and fourths. Half of 32, that's our starting place, is 16. 16 is a perfect fourth, so we're going to break it apart, make 2 4th root houses. The perfect fourth, 16, goes in the first house, 2 goes in the second, because 16 times 2 is 32. Now this w is to the first power. 1 does not divide by 4, and never can, so we put the whole thing in the little reject house, our second house. It's over the 4th root of 81. 81 is a perfect fourth. Okay, the 4th root of 81 is 3. So 3 comes out of that radical and just stays a nice normal number. The 4th root of 16 is 2. So the 2 comes out. So our final answer is 2 4th root of 2w all over 3. Okay, in this next section of our notes, we're doing something called rationalizing the denominator. Okay, the goal is to still get the radical term out of the denominator. Like on number 9, the square root of 5, again, cannot stay in the denominator. But what we did on our first 8 examples, we could either divide that radical term into another radical term in the numerator, or that radical term in the denominator like simplified to like a whole number on its own. And that won't happen anymore on these next set of examples. So we have a couple different ways we can rationalize the denominator. Now it depends on if our denominator is a monomial or a binomial. Mono means one term or one grouping. Now numbers 9 and 10 here, and I think 11 and 12, yeah, and 13, 14, okay, they are all monomial denominators. So the rule for them is that we multiply the numerator and denominator by the radical, or the number that's in the radical. And let's back up just a little bit. Now let's go back to like 5th grade math where we worked with fractions and how we could change fractions. If we had like the number 2/3 and I wanted to make it have a new denominator, and that denominator had to be 12, how would we change this fraction? We could only change fractions by multiplying, and I would have to multiply the bottom by 4, and if you recall, whatever we multiply the bottom by, we multiply the numerator by that as well. So you always multiply the denominator and the numerator by the same thing, and I know a lot of times when I would see this in like younger grades, they'd do something like this, like that's a number 1, okay? Where whatever you're multiplying the fraction by has to be equivalent of 1, meaning the top and the bottom are exactly the same. Now that's a universal rule with fractions. What you do to the denominator, you do to the numerator. So we are going to change our fractions now by multiplying. And what we won't need to multiply the bottom by, we have to multiply the top by that same term. Okay, and that term will be whatever is inside the radical. Because when you multiply two numbers that are same, whether they are underneath the radical or not, you get a perfect square. If you have a perfect square, you can square root it, and it makes magical things happen. So let's show that here on number 9 and 10. So we have 3 over 2 square root 5. Again, I can't get rid of this square root of 5. There's no numerator for it to divide into, and it's a prime number. Okay, I can't just break it down anymore. But if I multiply the bottom by the square root of 5 and the top, therefore, by the square root of 5, we can make some things start happening. Okay, 3 is a coefficient or whole number, and we're multiplying by the square root of 5. They're not in the same position, so we just kind of stick them together. It's 3 square root 5. Okay, remember, outsides with outsides, underneaths with underneaths. Okay, it is over 2. We have a coefficient of 1, makes 2. And now our underneaths are 5 times 5 is the square root of 25. Now in the numerator, 3 square root 5 can't simplify at all. Again, 5 is a prime number. We can't break it down. So the top stays the same. But in the bottom, and this always happens when you rationalize the denominator, if you're doing it right, this number is a perfect square. The square root of 25 is 5. That comes out. It multiplies with a 2 that was already out there. 2 times 5 is 10. See, 10 is doesn't have a radical on it. This is great. Now, this is done. You cannot divide this 5 and this 10 into each other because 5 is underneath the radical and 10 is not. They're not in similar positions, so they cannot reduce each other. Okay, so remember, outsides with outsides, underneaths with underneaths. Now, I could maybe see if 3 and 10 go divide or simplify into each other, but they do not. So this is finished. Okay, number 10, I have the square root of 8 over 15. Now I would check, again, the same process as above. Can 8 over 15 reduce? Can they work together? 8 over 15 does not simplify. Because they cannot work together, I have them work separately. So I think of this as two separate radical terms. The square root of 8 over the square root of 15. And 15 does not even simplify as a radical. It's made up of two prime numbers, 3 times 5. So it stays square root of 15. So I can't break it down. So the only thing I can do is multiply the bottom and the top term by the square root of 15. Again, if the top and the bottom are the same, they're equivalent to 1. So this is a legal math move. Because these are all radicands, we can multiply 8 and 15. They're both underneath the radical. They make 120 over. And the denominator, we have 15 times 15 is square root 225. And now we simplify each of these terms. Now 120, okay, if we took half of 120 to get a starting place on our perfect squares, we get 60. That means the first number we should test is lower than 60 on our perfect squares list, which would be 49. 120 divided by 49 doesn't divide evenly. And I'm just going to go through this quickly. Neither does 36, neither does 25, or 16, or 9. The only number that's a perfect square that divides into 120 is 4. And it's 4 times 30. That's the same thing as 120. And because we did 15 times 15, we should know that the square root of 225 is that same number, 15. No radical on that 15. It came out because it was two 15s that multiplied to make 225. In our numerator, we take the square root of 4. It comes out as a 2. So the numerator is 2. Then we had square root of 30 stayed in. 15 is our denominator, no radical in the denominator. And remember, 30 and 15 cannot simplify each other because 30 is underneath the radical. It's off limits. 2 and 15 don't have any common factors. They can't simplify, so this is done. Okay, let's look at number 12 here on the back side of our notes. Now I have the square root of 28a to the 5th power divided by the square root of 3a. Again, always check first to see if they can work together and simplify into each other. I would check, does 28 divide by 3? And it does not. Okay, so those numbers don't change, but I notice I have 5 a's in the top and 1 a in the bottom. We can simplify those. We could use our quotient rule. 5 minus 1, okay, we take out the 1 on the bottom, is 4. So we would rewrite this as the square root of 28a to the 4th over the square root of 3. Okay, now I can't have this square root of 3 in the bottom, and we already know that 28 and 3 do not divide into each other. So we're going to multiply the bottom by the square root of 3 and the top by the square root of 3. And the numerator, 28 times 3 makes 96. And we have a to the 4th power. And the denominator, 3 times 3, gives me the square root of 9. So now we're going to simplify the square root of 96. So half of 96, 48. Okay, so that means we're starting with 36 on our perfect squares list. 36 does not divide into 96. It doesn't divide by 25, 96 does divide by 16. So we'll break this apart as 16 times 6. And then my a to the 4th is a perfect square because 4 divides by 2. So that's how we break apart our numerator. The denominator, the square root of 9, is 3. So that's what the denominator turns into, just the number 3. And to finish up the numerator, my square root of 16, a to the 4th, square root of 16 is 4, and a squared comes out because 4 divided by 2 is 2. So our numerator is 4a squared, square root of 6, all over 3. Again, that is finished. On number 14, okay, we have 3 square root 2 plus the square root of 6 divided by the square root of 12. We have a binomial in the numerator. We still have a monomial in the denominator. So again, the rule is if you have a monomial in the denominator, you multiply the top and the bottom by that radical term. So we're going to multiply the numerator and the denominator by the square root of 12 over the square root of 12. So because the top is a binomial, we have to distribute that numerator in. So we have 3 square root 2 times the square root of 12. Okay, so outsides go with outsides, underneaths with underneath. So we have 3 on the outside, and then 2 times 12 are the underneaths. They multiply to make 24. Plus, then we do the square root of 12 times the square root of 6. They're both underneath. They're both radicands. So 6 times 12 is 72. This is over. Square root of 12 times the square root of 12 is the square root of 144. Okay, now we have to go through and simplify our numerator. 3 square root 24. Okay, this first term. 24. Which perfect square goes into 24? That would be 4 and 6. So this would be 3. And we're going to say this is 4 times 6. And say plus, the square root of 72. Half of 72 is 36. And 36 is a perfect square. So we have 36 times 2. Now what is this all over? The square root of 144 is just the number 12. Now let's simplify this numerator a little more. The square root of 4 is 2. It multiplies with 3, so we have 6 square root 6. Plus, then we have the square root of 36 is 6. We have 6 square root 2. These are not like terms because their radicands do not match. Okay, they're fully simplified as radicals, and this is all over 12. Now, when we check to see if this simplifies, we have 2 fractions, 2 numerators over 1 denominator. Okay, written as 1 fraction. So we're checking 6, 6, and 12. A number has to go into all 3 of those. We can't touch our radicands right now. Okay, they're off limits. Only another radicand could simplify with a radical term. So what number goes into 6, 6, and 12? 6. So we're going to divide all 3 of those that have a little blue dot underneath by 6. So we have 1 square root 6 plus 1 square root 2. And 12 divided by 6 is 2 in the denominator. Again, you cannot touch these radicands, the square root 6 and square root 2, because it would have to be another square root in the denominator term that would divide into them. And we don't have that, so this is done. Okay, so these last few examples that we are going to do, we have binomials in the denominator. Okay, so these are binomials because there's 2 terms. So when we have 2 terms in the denominator, the only way we can get rid of the radical that's in the denominator and messing everything up is to multiply by the conjugate. Okay, so let's write that down. Multiply by conjugate. Now we did this when we dealt with imaginary numbers. Conjugate means you have the same expression, but you just change the sign in the middle. And again, it's the conjugate of the denominator we're working with right now because we're not allowed to have a radical in the denominator. So if we have 4 plus the square root of 2, the conjugate would be 4 minus square root 2. Change the sign. And then that same rule, what we do to the denominator, we have to do to the numerator. Okay, we're multiplying top and bottom by the same expression. So here we go. In the numerator, we're going to distribute 4. 4 times 4 is 16. Then 4 times negative square root 2 is negative 4 square root 2. Over. We have to FOIL. When we're using the conjugate, we always FOIL in the denominator for sure. So 4 times 4 is 16. 4 times negative square root 2 is negative 4 square root 2. Then we come back to the insides. Square root 2 times 4 is plus 4 square root 2. And then last, we would have square root 2 times negative square root 2 is negative square root 4. Now let's see if our numerator simplifies it all. In the numerator, we have 16 minus 4 square root 2. These, again, are not like terms. Think like 16 minus 4x. Okay, they're not like terms. We can't do anything with it. We can't do anything with this 16 minus 4 square root 2. They don't simplify either. So that's going to stay the same. Now, the awesome thing about the conjugate is it always turns the denominator into just a regular number with no radicals. Because look what we have here in the middle. We have like terms, but they have opposite signs. Negative 4 square root 2 and positive 4 square root 2 cancel out to 0. The last term, that's a radical term, should always be a perfect square. The square root of 4 is 2, so that was a minus 2. There was a minus sign in front of it. And it combines with a 16. 16 minus 2 makes 14 as a denominator. Look at no radicals in the denominator, which is super awesome. And then we check to see if we can divide our regular numbers or those coefficients. We have 16, 4, and 14. Okay, again, do not touch that radicand of 2. There's nothing that we can do to change that number at this point. These all divide by 2. So 16 divided by 2 is 8. Negative 4 divided by 2 is 2. The square root of 2 stays. And 14 divided by 2 is 7. And this is a simplified answer we want. And again, if you're in class, I know your calculator actually does all of this. If you type this into your calculator, okay, it will actually spit this out. Use it to check on your test. I will not give you credit for any of these problems if you do not show your work, and I will stick to that. So understand what a conjugate is. Remember how to FOIL. Remember your rules with multiplying with radicals. Otherwise, you won't get credit on the test, and that would be so sad for you. Okay, on 17, we have the square root of 3 divided by 1 minus 4 square root 2. Okay, I have a binomial in the denominator again. The only way to get rid of it is to multiply by the conjugate. We have a minus sign here, so we're going to multiply by 1 plus 4 square root 2. That's our conjugate. And when we do the bottom, we have to do to the top. So now we're going to distribute in our numerator. The square root of 3 times 1 stays the square root of 3. The square root of 3 times 4 square root 2. All right, remember our rule about positions when we multiply with radical. The coefficient here and for the square root of 3 is like a 1. So we have 1 times 4 is 4. The square root of 3 times the square root of 2 is the square root of 6. Okay, over. In the denominator, we're going to FOIL. So 1 times 1 is 1. 1 times 4 square root 2 is 4 square root 2. And the inside, we have negative 4 square root 2 times 1, so minus 4 square root 2. And then negative 4 square root 2 times positive 4 square root 2. Negative 4 and positive 4 make negative 16. And 2 times 2 for our radicands makes the square root of 4. Now in the numerator, I check to see if anything can simplify. 3 is a prime number, so the square root of 3 cannot change. 4 square root of 6, even the square root of 6, even though it's even, 6's only factors besides 6 and 1 are 2 and 3. So it only has prime factors, so it can't change. And 3 and 6 as radicands are not like terms, so they will stay separate. Okay, our denominator. Okay, again, because of the conjugate, this always happens. The middle two terms cancel out. The last radical term should be a perfect square. So the square root of 4 is 2. It multiplies with negative 16 to make negative 32. 1 minus 32 is negative 31. And you know what? I do not even like negatives in my denominator. So how can I get rid of this negative 31? Because nothing else can simplify. If you said it, you were right. We divide by negative 1 to all three terms. So this would be negative square root 3 minus 4 square root 6 over positive 31 now. And that's the best way to write our answer. Okay, and the last example I'm going to do is number 19. We have a binomial on the top, 3 plus square root 7, divided by 2 plus the square root of 2 plus 2 square root 7. We have a binomial in the numerator and a binomial in the denominator. Remember, you multiply always by the conjugate of the denominator when you're simplifying radical terms. It's the denominator where we have the issue. So we will multiply by 2 minus 2 square root 7 to the denominator and the numerator. Oops. All right. So we have to FOIL the top and we have to FOIL the bottom. So here we go. We have 3 times 2 is 6. 3 times negative 2 square root 7 is negative 6 on the outside. Square root of 7 stays underneath. And then the square root of 7 times 2 would be a positive 2 on the outside, square root of 7 on the inside. And then square root of 7 times negative 2 square root of 7. Okay, the negative 2 is on the outside, and 7 times 7 is 49. Over. Okay, we're FOILing in the denominator now. So we have 2 times 2 is 4. 2 times negative 2 makes negative 4, and square root of 7 is underneath. Then we have 2 square root 7 times 2, so plus 4 square root 7. And then 2 times negative 2 is negative 4. Square root of 7 times square root of 7 is square root of 49. And hopefully you're getting to the point where you see numbers like you're writing down square root 49, and you should know that number is going to change. Okay, the square root of 49, that's a perfect square. Square root of 49 comes out as a 7. So in the numerator, it comes out as a 7 right there. It multiplies with negative 2 to make negative 14. We have 6 minus 14, which is negative 8. Now the middle two terms here, they're both like terms because they have square root 7. So we put together their coefficients. Negative 6 plus 2 is negative 4, and then it stays square root 7. Okay, it's all over. Okay, the middle two terms again cancel out when we did the conjugate. That square root 49 again comes out as a 7. We multiply 7 and negative 4 to get negative 28. That negative 28 will combine with positive 4 to make negative 24. Now to simplify this, we need a number that goes into negative 8, negative 4, and negative 24. And that will be negative 4 because we don't want to leave that negative in the denominator. So negative 8 divided by negative 4 is positive 2. And then negative 4 divided by negative 4 is positive 1, square root 7. And negative 24 divided by negative 4 is positive 6. And this is fully simplified. We can't divide this 2 and 6 because remember, when you have more than one numerator, everything in the numerator, all those coefficients have to divide by the denominator. Square root 7 has a coefficient of 1, which will not divide by 6, so therefore we are done. All right, remember all your rules when you're working on Excel. Okay, 6.3, there's 10 questions. Don't get behind, you can do it. We're so close to our final. Stay on top of your work. Good luck.